Um, this is our mass spring damper system, and I drew the free body diagram, and this is our free body diagram, which is the diagram telling us the forces acting on the system, which is the mass. Right now you have to isolate the mass, and the coordinate is x, means this is moving with this coordinate x, and if you rearrange these terms, mx double dot, this is the equation of motion of mass spring damper system. And if we normalize the acceleration term, then the second order differential equation looks like this. And if you compare with the standard second order differential equation, then if you compare these two equations, equation 1 with equation 2, so the coefficient of the second order terms gives us not much information, but coefficient of velocity. Let's compare the coefficient of velocity c over m on the left hand side from equation 1 to zeta omega n from the left hand side, from equation 2, and the coefficient of the displacement from equation 1 is k over m. So here zeta is the damping ratio c over 2 m omega n, and natural frequency is square root k over m. Do you understand that? Please write down this formula. This is the, and damping ratio is actual damping over the critical damping. Cc is the critical damping, and the formula for critical damping is 2 m omega n. Are you guys noting down? I want to show different cases when zeta is less than 1, the system is known as underdamped. When zeta equals to 1, system is critically damped. And when zeta is greater than 1, system is overdamped. And I want to show you the graphical representation. If there is a mass like this mass, if you give initial condition like 2 centimeter and leave it, so how will it behave if zeta in these three cases? If zeta is less than 1, you bring the mass to 2 centimeter here and leave it here. It will come down, and due to inertia it will go up and come down. So when you see certain oscillation about the mean position, this is the mean position, which is I think this is 0. Okay, so when you bring the mass here to the right and leave it, the mass will come back to the mean position, but it will not stay there. It will go back further because of the inertia, and then come back towards the mean position, back and forth until it becomes uh, until it is at the mean position. Do you understand this graphical representation of the mass under the when zeta is less than 1? Now I want to show you another example. When you, in this case, when you bring the mass here, then it does not oscillate about the mean position, but it actually it comes back to the mean position. This is zeta equals to 1. And when you have another situation, when you bring it to 2 centimeter and leave it, it will come to the mean position a little bit longer time. This case zeta is greater than 1. This is overly damped, over damped system, critical damped system, under damped system. You will perform this experiment today with the damper and without the damper. So let me